In this section, we'll discuss about substituent group effect in determining the product formation. Now, in order to explain this, I'd like to go over problem number 34, chapter 5, page 183, and this is 7th edition of Fundamentals of Organic Chemistry by John McMurray. So the question asks you to predict the major product of mononitration. Now, what is mononitration? How do I get NO2 group to react with the benzene ring? So that's what I'm going to show you next. You need to take strong nitric acid or concentrated nitric acid in presence of concentrated sulfuric acid gives NO2 plus and H2O. In book, this reaction is shown. This NO2 plus is very important for nitration of benzene ring, and that's what we're going to show you in this particular problem. Part A, you begin with bromobenzene. So bromobenzene would have a benzene structure. So that benzene, at any one of these positions, you can write down Br, that's bromobenzene. And then you are adding, for mononitration, you need to add this NO2 plus, which is positive charge, and that would be attracted to the benzene ring because benzene ring has lots of electrons and NO2 has positive charge, so it's electrophile. So NO2 is electrophile and benzene ring is nucleophile, so there has been attraction to each other. So now the question is, there are several locations NO2 plus can go. So I'm going to show you these two locations, which are called ortho and para, shown with red asterisk, and I'm going to show you other position, which is the meta location, shown with blue asterisk. Now the question is, out of these three possible places, where would this NO2 plus go? Now we can, if we understand this topic, we can quickly predict our answer. When you have BrClI with pairs of electrons, lone pairs of electrons, it would be ortho-para. So in other words, you're going to get two different products in this case. So let me write down that. So this is the benzene ring, Br. Now I left out the electron pairs now on Br. So I can have either this product, actually would have a combination of two products. One would be the ortho product, the other would be the para. So this is Br, and the para location, you'd have NO2. Remember, 1, 2 is ortho, 1, 4 would be para location. So this is ortho isomer, this is called ortho nitrobromobenzene. This one is called para bromonitrobenzene. You do not get any meta. Even if you get any, that would be very small quantity. So in other words, Br as a substituent group favors ortho-para direction. So we call it ortho-para director. So Br with unshared electron pair would be ortho-para director. So now we can generalize this. Any atom coming from a group of atoms, if it has any unshared electron pair and it is directly bonded to benzene ring, then it would be ortho-para director. I can give you several other examples, and right now let's go over the next problem. The next problem is on benzonitrile. That's part B. So let's draw a line here. So benzonitrile, again you have a benzene ring, 6-membered ring. It's same as cyanobenzene, so that means you have a cyanide group. Keep in mind a neutral carbon must have 4 bonds, so I must have triple bond here, CN, as it is attached to benzene ring. It would have a triple bond, and then nitrogen would have also a pair of electron. Now I'm attaching the same group now, NO2. So this is the plus NO2 group. Question is, where would this go? Again, I'm going to write down with red asterisk ortho and para possibility, and with the blue asterisk going to write down the meta location. Again, just like before, this time it is also would show preference for a particular direction. Now, this is something you need to examine carefully. The carbon that is bonded directly to the benzene ring, does it have any unshared electron pair? Answer is no. Not like Br, where we had unshared electron pair sitting on Br. Here there is no such unshared electron pair because all these electrons are being shared. Secondly, is it an alkyl group? Answer is no. So when you have unshared electron pair, or if it's an alkyl group, then it would be ortho-para director. Otherwise, it's going to be meta director. So in this case, this is neither alkyl group nor the group where the first bonded atom to the benzene ring do not have any unshared electron pair. So it's going to be meta director. So I'm going to write down this as a meta director. So the final product is going to be C triple bond N, and then this will be meta director, so it's the meta position out of NO2. Now I'm going to do next part E, phenol, and I'm running out of space on this slide, so I hope this would give you a good idea about how this reaction happens. Phenol, you need to know, phenol, it'd be 6-membered benzene ring with OH. You need to remember these common names. Now, if you write down carefully, OH has O and H. There is one bond. I think let's redraw this because it doesn't look that clear. As I'm running out of space, it'll be hard for me to even write down. This is OH. And here you'd have unshared electron pair. And I think I could not draw the double bond that well somehow. But you probably understand that this benzene has 3 double bonds. For some reason the third one I could not draw too well. Okay, now this is going to be added to NO2 plus. So this is NO2 plus. Question is, where would that NO2 plus go in this case? Again, we are going to focus on substitution group OH. Is it an alkyl group? Answer is no. Is it a group where the first directly bonded atom to benzene ring has unshared electron pair? Yes. Whenever you have an unshared pair of electron, 1 or 2 or 3 pairs of electrons, those would be ortho-para directors. So in this case, NO2 would be attached to 2 locations. One would be the ortho, the other would be the para location. So let me, if I can, I think I have left to squeeze in everything. 2, 4, 6. So now I have OH. Now I am not showing any more those electron pairs because I'm done with my the reason why I wanted to show you that. NO2, that's one of the products. The second product would be the para. OH and NO2. So these are the two products you're going to get. The left hand side one is the ortho isomer, the right one is para isomer. The name of this is left hand side one is orthonitrophenol because this part is phenol. And the other one is paranitrophenol because of the para location. Here I'm showing you just to remind you, how do I quickly determine which would be ortho para directors and which one would be meta directors. I already mentioned that to you, but now this would be more understandable to you. So follow the color, the red ones, you can see that red ones, we say ortho para, and let me show you that this is ortho, this is para. In order to get ortho and para, you must have lone pair of electrons or alkyl group. What I could not write down here is directly bonded to the benzene ring. So that means atom that is directly bonded to the benzene ring, you have to carefully look at it whether it has unshared electron pair. So NH2 has unshared electron pair. Now in case you are wondering that how do I know that NH2 would have an unshared electron pair? So I'm talking about something like this. Benzene ring and having NH2 bonded there. I hope you would know the name of this compound. It's called aniline or aniline. I think some people would pronounce this as aniline. So anyway, this nitrogen, this is the neutral, whole thing is neutral. So nitrogen has 3 bonds, and don't forget it must have a pair of electrons to have 8 electrons around nitrogen. So by doing that, you already know that NO2 is a group with unshared pair of electron, and when nitrogen is bonded directly to benzene ring, and that nitrogen has unshared electron pair. That means it would be ortho para director. So this group is going to be ortho para director. Now that's why you can follow that this is going to be ortho and para director. I'm showing you in this diagram. Similarly, OH should be ortho para director. If you follow the color, you'd see that. Alkyl group, even though we're not explaining it, is called hyperconjugation. I think in the next level of organic chemistry, you'd see why alkyl groups are ortho para directors. Right now, you just remember that. Cl and Br, each would have those unshared electron pairs. I've already shown you example of Br, and that's why these are also ortho para directors. So whenever you have a substitution group, always think about the substitution group and the atom that is directly bonded to the benzene ring. If it has unshared electron pair, then ortho para directors. If it is an alkyl group, you remember the alkyl group. By removing hydrogen from an alkane, you get alkyl group. It would also be ortho para director. All other groups would be meta directors. With that in mind, let's try to do number 34, F. And I will squeeze in that on the top. This is F, 34F. Question is about benzaldehyde. I'm sorry that I'm making it a little messy here. Benzaldehyde is CHO. So you'll have to remember these names. Now, unless you explicitly write down CHO, you would not be able to answer this question whether it's going to be ortho para or meta director. Because you need to know whether the carbon which is directly bonded has any unshared electron pair. So let me draw it again and in a manner so that you can explicitly see the bonding. So here is the C. This is the C directly bonded. Now CH. Remember, hydrogen can only have one bond. So I have no other choice. Oxygen has to have the double bond. Again, my bonds are a little bit drifted. I think it's because I ran out of space here. So let's carbon. So this is here is CH double bond O. I hope you can see that, or maybe I think I should rewrite again to give you a better idea about CHO bond. Just let me write down the CHO, because that gives me more space. So that's the CHO. So again, we are asking the same question. This is benzene ring is here. Does the carbon which is directly bonded to the benzene ring has any unshared electron pair? Answer is no, because all these electron pairs are being shared. Is it an alkyl group? No, this is not an alkyl group. So when both are no, it cannot be orthopara. So it has to be meta-director. So the question F, where you're adding NO2 plus, NO2 plus will have to go to the meta location of benzaldehyde. So your final answer to this question is going to be CHO, and NO2 has to be the meta location. Meta could be, I can write down the right side or left side, doesn't matter, as long as it is 1, 3. So that's the final product you're going to get in the meta attachment. Now, in case we're wondering, what is going to be alkyl group, in case you forgot about it. This is an alkyl group. I'm going to show you that. C, this is isobutyl group, and I just left out hydrogen. So just focus on this. Is it an alkyl group? Answer is yes. If your answer is yes, that means it would be ortho-para-director. That means NO2 plus, if that gets bonded, it would be at ortho or para location, not in meta location. Next, I want you to pay attention to the difference in color in this particular slide. Now, some of these are shown in green. Now, those are called deactivators. So there are a couple of those in orthopara directors also. They're deactivators. Now, why they're deactivators? They're highly electronegative elements, like let me show you with Cl. So when Cl is bonded, we call it induction effect. Since it is highly electronegative, it's going to pull electron away from the benzene ring. Remember, I mentioned that electrophilic substitution takes place readily because of the fact that benzene ring has all these loosely bonded electrons, pi electrons. Now, if there is a substitution group which pulls electron away from the benzene ring, that means benzene ring would not show that kind of reactivity. And that's why we call them deactivators, because they're usually highly electronegative element. Some of them could be orthopara directors like ClBr. They're all orthopara directors, but they're deactivators because they are electronegative and they would suck electron out of the benzene ring, quite a few. And all these meta directors, they would all attract electron out of the benzene ring. And that's why all the meta directors are basically deactivators. Now you may be thinking, how does it happen for COOH? I mean, because carbon is not that electronegative, but if you look at COOH, that causes this change. So this is the benzene ring, and I have C double bond O, OH. Even though carbon is not more electronegative than the other carbon in the benzene ring, but these oxygen attached to carbon are highly electronegative, so they'd be basically pulling electron away, and that in turn sucks electron out of the benzene ring, and that's why it becomes deactivator. So keep in mind, all meta directors are deactivators, and among orthopara directors, some of the highly electronegative ones, ClBr, would be deactivators. OH is not, because OH is not same as O. If I had only O, then that would be deactivator, but you have OH, so it's different than O. So don't get confused. So here we learned about activators and deactivators. NH2OH, they are activators or alkyl group. That means they enhance first thing is they don't suck electron out of the benzene ring. And secondly, because of their extra electron, unshared electron, sometimes they release electron towards benzene ring. So benzene would be even richer in electron and would show greater reactivity. And that's why they're called activators. So far, I asked you to remember that whenever a substitution group has an atom that is directly bonded to the benzene ring with a lone pair, then it would be that substituent group is going to be ortho-para-director. And when there is no lone pair or it's not an alkyl group, then it's going to be a meta-director. The question is there any way to explain it rather than just remembering those facts? So we are going to discuss this by going over resonance, and I'll also go over one of the homework problems, which is number 14, page 171. But before I go over the homework problem, again, I want to remind you about resonance, when it is possible and when it is not. So let me give you a simple example, then you'd know for your that whether it's resonance is possible or not. Again, I'm considering a 6-membered ring. This time I have double bond in just one place. And let's fill in with hydrogen so that would allow me to understand it better. I have one hydrogen here. Let's draw a line here. I have one hydrogen here. Remember, carbon must have 4 bonds. That would give 4 bonds. Now this must have 2 hydrogens. Each of the other ones must have 2 hydrogens. Again, I don't have much space here to show you this, but I think this is the best place to show so that you have the concept of resonance. Now, you may be thinking, okay, I have a pair of electrons. Can I move it to the next carbon? Let's try that. If you're moving it, what happens that, let's redraw. And I'm going to draw a line here. Okay, and now I would have benzene ring. Okay, that's the benzene ring with all these double bonds, single bond, double bond. And I think I need to redraw it because I just don't have enough space. So let's draw it at the bottom. I have more space here, so okay. So now I have one hydrogen here. Keep in mind, resonance should not move any atom. So atoms should remain intact in order to be a valid resonance structure. I have 2 hydrogens here, and then I have 2 hydrogens here, and I have 2 hydrogens here. Okay, because I didn't exceed any. Now keep in mind, I moved the double bond from its original location to here. So this is the new location. Now as a result of this, see what had happened. I'm going to show you with blue ink. Focus on this carbon. 1, 2, 3, 4, 5. You cannot exceed 4 bonds, so it has 5. And the question is, when you have 5 bonds, how can it get rid of 1 bond? Is that possible? If you get rid of hydrogen, you may think that would be possible, but that would not be acceptable because you're moving an atom. So whenever you move an atom out of that molecule, it's no longer a resonance structure. So in order to be a valid resonance structures, all the atoms will have to remain intact. So in other words, this kind of resonance structure is not possible. So that's wrong. So keeping this in mind, we are going to draw resonance structures and explain to you that why unshared electron pair on an atom which is directly bonded to the benzene ring would be ortho-para-director. Now this is the specific problem that which we'd like to go over. Why is methoxy group an ortho-para-director? So let's first focus on that. Now this is the benzene ring. Methoxy group has O and CH3. Now I can quickly assign electrons because this is like OH attached to the benzene ring. H is replaced by CH3. Remember I said oxygen, neutral oxygen would have 2 bonds and 2 pairs of electrons. So that gives 8 electrons around oxygen. So that's methoxy group attached to benzene. Now keep something in mind here that so far we have been telling you to remember that whenever you have a situation like this where oxygen has unshared electron pair, it will be ortho-para-director. Here we are going to explain that by going over this particular problem, which is number 14. So let's go over number 14 from chapter 5, so 5.14. This is on page 171. So the question is, draw resonance structures of the 3 possible carbocation intermediates and show how a methoxy group directs bromination towards ortho and para positions. So bromination, remember that bromination would involve Br plus because that would be attracted to the benzene ring. Let's now attach it to ortho location of this carbon. So in other words, you're going to attach this bromine to ortho location of the benzene ring, and that would give you the following structure. Sorry that my benzene doesn't look too good. Okay, I have now OCH3 and I have Br here. Keep in mind that bond was used in attaching the Br, so that bond would be gone. So this is gone. Now when this is gone, Br came with positive. Positive charge has to be somewhere because you cannot destroy the charges. And from formal charge calculation, you'd find that positive charge is here with this carbon that has oxygen. Now question is there any other resonance structure possible? Answer is yes. There are quite a few other structure possible. So I'm going to draw those and I'm going to show you how that's possible. So let's have a double arrow is shown for resonance structures, and I'm going to draw the next structure. Okay. Now, before I draw the new structure, let's make sure that I haven't moved any atom. So Br was in ortho position. We have O, CH3, and O had those 2 pairs of electrons on it. Now, the double bond, the bottom one, remain intact. Now, this double bond, let me show you with the red arrow, can move to that next carbon. And if that happens, that means you'd have a double bond in here, the new double bond in here, and positive charge moves to this carbon. Let's write down here. Okay. So this would be resonance structure number 2. Is there any other structure possible? Yes. Again, you can see that positive charge would try to, positive or negative charge would always like to get distributed as many positions as possible if it can easily go from one location to the other. all the resonance structures we are showing you here, there is an easy passage. That means we are not removing any atom in order to do that. So now the pi electron from this bond goes in between those two carbon, where one of the carbon has positive charge. So now you have a new structure. Let's try to use the same color. New structure. A double bond here. Now the new double bond is in here now, and the positive charge moves over here. You can either calculate formal charge, or you know the fact that that particular carbon has lost the double bond. And remember, you cannot move anything out of this molecule, so must have everything else intact. OCH3. This is going to be our resonance structure 3. Out of this resonance structure 3, one is particularly more stable. Let me show you why. That positive charge is on the carbon, which is attached to the electron, which is attached to the oxygen, which has lots of extra electrons. So remember that positive charge, it gets, because of the induction effect, its charge gets stabilized, because this oxygen can release electron towards this positive charge, and that's the stabilizing factor. That the more ways you can distribute this positive charge or reduce the charge density, positive charge density on any center, because these electrons are going to help that positive charge. So I would say that one is particularly stable, the more stable than the other ones. So write down on the top, this one is more stable. Why more stable? Because it's that carbon which has the positive charge is directly bonded to oxygen with two pairs of unshared electrons, and it allows some of this electron cloud to move towards the positive and reduce that positive charge density. Is there any other structure possible? Answer is yes. There is a fourth structure possible. Even though the question is asking for 3, I'm going to show you the fourth one, and that way you'd know what's all the possible ways you can distribute positive charge. Let's get the same color. I think I didn't want to draw a double bond here. So this is just a 6-membered ring. Okay, I'm redrawing first the number 1 with the double bond. I'm not changing their position. What I'm going to show you next is this oxygen, CH3. It has electron pairs, and remember that this, I'm showing you with an arrow. Focus on structure number 1, electron pair. In order to generate the new structure, electron pair goes in between oxygen and carbon of the ring, and makes a double bond there. So in other words, this electron pair would no longer be there, rather there'll be a double bond. Let me make a double bond here. So I would no longer have positive charge on that carbon, rather that charge would be moved to oxygen. Now you can always count to make sure that you understand it. Let's count around oxygen. There are 2 electrons solely on oxygen. Then third one is coming from this bond. And 4 and 5 are coming from the double bond. Neutral oxygen is supposed to have 6 electrons, 6 valence electrons, and it has 5, so it's +1. So these are the 4 resonance structures. And remember, I got 4 from 1. So there are four ways I can distribute the positive charges. In addition, number one is particularly more stable because of the electron release from an atom which is directly bonded and which is rich in electron. So because of all these resonance structures, this ortho attachment of Br will be highly favored. If you try the meta attachment, you're not going to get that many structures. Let me show you quickly how would it look like if there is a meta attachment of Br. Of course, I'm running out of space here, so let's try my best to show you at least a couple of structures with meta attachment. Again, we're going to deal with the same compound. Even though this particular question doesn't ask for showing you meta attachment, but I'm just showing you so that you understand how this problem can be done so that you can do yourself number 15 or similar other problems. CH3. Okay, now assume that Br plus is now attached to the meta location. So this is the meta location, so it's getting attached here. So the double bond will be broken. So what are you going to get? OCH3, and now I have the meta Br in meta position. Keep the other double bonds intact. Now since Br got here, positive charge would be here. Now can I have any resonance structures? Yes. This positive charge, because of this resonance, the double bond would be coming in between, and if that happens, let's show you that the positive charge is going to move to a different location. So I'm going to show you that. Now this double bond is remaining intact, Br is remaining intact, and OCH3 is going to remain intact. And since I moved this one of the double bonds, the double bond, new position of the double bond is here. So that carbon would no longer have positive charge, rather positive charge would now move to this carbon. So this is going to be structure 1, this is going to be structure 2. You would have only one more structure. And I'm going to show you with blue arrowhead starting from structure 2. This comes down here. So then my positive charge moves to, since I ran out of space, I'm just showing you location of the positive charge in the third place. So these are the three possible resonance structures for meta attachment, whereas in case of ortho attachment we got 4. In para attachment you will also get 4. Not only 4, one of those structures is particularly more stable than the other one. So more resonance structures means better distribution of positive charges and greater stability of that intermediate carbocation, and nature favors that. So in other words, ortho-para attachment will be favored here. Similarly, you can do number 15 if you try for understanding this. I have shown you this slide before. Again, I'm bringing it in here. Now, on the right hand side, you see charge mass distribution is not good, and that's why the whole structure is falling down. On the other hand, on the left hand side, this structure is quite stable because mass is distributed quite well. Charge distribution would have the same effect, or resonance would have similar effect. If there are more ways charge could be distributed to different centers, you'd expect stability, and that's why more resonance structures would give you greater stability to that particular carbocation, and hence product formation, because nature always favors something more stable. In this slide, we're going to discuss when there are two substituent groups attached to the benzene ring, how would I determine where would my group would be heading in product formation. In order to explain that to you, I would like to go over homework problem, which is number 38, page 184. Now, the question tells us the predict major product you'd expect to obtain from sulfonation of the following substances. A is on chlorotoluene. So let's write down A, orthochlorotoluene. So this is toluene. You have to know these names. Methyl benzene is called toluene. And in ortho position you have chloro. Remember chloro having all these electron pairs? Let me remind you what's going on here. I have an alkyl group which is ortho para director. I have chloro group which is also ortho para director. But they are not identical in activating or deactivating the benzene ring. So methyl group, let me write down here, methyl group OP director, Cl with electron pairs, also OP directors. So both are OP directors. Alkyl groups are ring activators. So let me write down here activators. That means it enhances activity of benzene ring. On the other hand, chloro group, Cl group, because of its electronegativity, it pulls electron out of the benzene ring. We call it inductive effect, and it's a ring deactivator. So this is deactivator. So the rule is when you have an activator and a deactivator, then the activator is going to dominate and directs the new group to the right position. So in this particular case, they're asking about sulfonation. Sulfonation means addition of SO3H plus. So that's going to be attached. Now we need to figure out where it's going to get attached. Now, in this case, CH3 is ring activator, Cl is deactivator. Since the rule says that activator is going to dominate, so the product would be dominated by alkyl group. Now alkyl group would then direct SO3H group to two positions only, which is ortho or para position to alkyl group, as if Cl is not there. So that's the kind of products you'd expect. So I'm going to write down those two possible products. CH3, and then here you have Cl, and then you'd have SO3H. Let's write down here SO3H. The bonding is through sulfur. That's one of the products. Let's call it product number one. The other product would be again, I must keep intact CH3 and Cl, and this time OH would be in here, para to alkyl group. That's 3H. So that's product number two. You're going to get both the products. However, from a different consideration, what we call steric hindrance effect, product would be smaller in, one would be smaller in quantity, smaller amount, and two would be larger in amount. Why? These groups, if you make a molecular model, you see that these are big groups. They're so close to each other, even though they would be directed. I mean, alkyl group is going to direct SO3H to the ortho and para position, but ortho position is so crowded, so not too many of SO3H would go to that position. So para would be most dominant in this case. But keep in mind you should write in both 1 and 2, but because of a steric hindrance, 2 is going to dominate. In the last slide, we're going to talk about another homework problem, which is number 58, page 187. This is on synthesis. That means how do I go from reactant to a product? I'm just going to show you part of these. So number 58, I'm not going to do the whole thing because I don't have even enough space here too. So this is on page 187. So your benzene ring. So your benzene ring. I'm drawing exactly the way it's shown in the book. And they're saying it's A, and they're telling you the product. Double bond, single bond, double bond, double bond. And you see an attachment of CH2, CH3. Basically, what do I need to add here in order to get this first product? This is how you'd figure out. First, think about what you added, what kind of group you have added. This is an alkyl group. Then you think about the method. How do you use alkyl group? Remember, we talked about Friedel-Crafts alkylation. So you can have this compound, CH3, CH2, Cl. And you need to have AlCl3 as a catalyst. And AlCl3 is going to remove that Cl and make CH3CH2 plus. And that CH3CH2 plus is going to get bonded to the benzene ring, and that would give you this product. Next, they're asking that how do I go from this product to the next one, which is bromination product. So this is CH2, CH3, and in ortho position I have Br. First, we need to know what kind of group is this. This is an alkyl group, so it's going to be ortho para director, so there's no problem. So I just need to get the right molecule or right reagent. So what is going to be B in this case? We are attaching a Br. So now we think about how do I add Br to a benzene ring in a substitution reaction. Remember, we talked about Br2. From Br2 you need to generate Br plus. So you need to have a catalyst. So Br2 needs FeBr3 because that creates Br plus, and that Br plus gets bonded to the benzene ring. And why it's going to be give you ortho? Because this alkyl group is ortho para director. So basically you're going to get two products. One will be ortho, the other one will be para. Even though the question is asking for only ortho, but keep that in mind. This is the ortho product plus the para product. The para location I'm showing you with a red asterisk. This is the para location, because these are all relative to alkyl group, because this is 1, 2. 1, 2 is ortho, 1, 4 is para. Next, they're asking how to go from here to this compound. Let's use this double bond, single bond, double bond. This time I have COOH or CO2H, is the same thing, and Br. Now you think about first what had happened to the original molecule. Original molecule has an alkyl group, but my final product doesn't have an alkyl group. In that position I have a carboxylic group. So what do I need to add? Now you need to know those reactions. Potassium permanganate, KMnO4. KMnO4 is going to change any alkyl group to carboxylic group. So keep that in mind. So neutral KMnO4 is going to convert alkyl group to carboxylic group. And the last step is I think I first thought that I would not have enough space. Now I think it seems that I would have space. So I can draw the last step. This is the benzene ring. Okay. Now let's first write down CO2H, CO2H, and Br in ortho position, and SO3H also being added here. SO3H being added. But the question is, how do I add that SO3H? Now it's easy. You need to get SO3, generate SO3H by adding SO3 and sulfuric acid. You see that in the book that creates SO3H plus. Then it's got bonded to the benzene ring. Now where would it go? Now both are deactivators in this case. So really there is no preference here. CO2H is meta director and deactivator. So Br is, even the ortho para director, is also deactivator. So that this reaction would not happen at a fast pace. It would be a slow reaction, not a very highly favored one. So according to your experimental condition has to be changed, because benzene structure would not show much reactivity. So if you look at Br, SO3H would be either in ortho position or Br position. So let me write down asterisk. Again, ortho position, if it goes to ortho position, it will be very crowded. So it will try to avoid that. So the para location will be better in terms of Br. Or meta location from CO2H, and that's the meta location. It just happened in this case, para location of Br is same as meta location of CO2H. Sometimes they could be in different locations. In that case, you get mixed products.